Hey, welcome back. In this chemistry video, we will be discussing polar bonds between molecules and intermolecular forces. Certain molecular compounds do not share their electrons equally, so they exhibit a property known as polarity, and polarity can also lead to two different molecules not being bonded together, but attracted towards each other. And that's what intermolecular forces are. So, when the electrons are shared between two atoms, each atom's nucleus, by virtue of having protons, exerts a pull on those electrons, but it's not necessarily an equal pull. An atom with a larger nucleus has a stronger attraction to those shared electrons. So those electrons will spend more of their time surrounding the larger atom, the atom with the larger nucleus, than the other one. It's not a fully ionic bond. There is a point where two atoms have such different electronegativities that they permanently form an ionic bond, or the electron permanently transfers over. But with molecules, it's a sharing because it's a covalent bond, but it's an unequal sharing. So pure elements that form molecules like O2, N2, hydrogen, chlorine, there's no polarity between them, because each atom has a nucleus exactly the same size in terms of proton number, so the electron is perfectly shared between the two of them. So there's no polarity whatsoever. But a polar covalent bond occurs when we have a large difference between the nuclei of two atoms. So when we look at the nitrogen atom here, we just want to imagine, because the nuclei are the same size, that the triple bond, the three pairs of electrons that are shared between them, will orbit back and forth evenly. The electrons have an equal probability of being next to this nitrogen atom or that nitrogen atom. Now with water, which we'll discuss in more detail shortly, with water that's not the case. The electron is more there are pairs of electrons. The pairs of electrons are more likely to be found closer to the oxygen atom than the hydrogen atoms. So that's why we have a negative sign over there and a positive sign over here. Electrons are negatively charged, so this gives water slight polarity, kind of like a magnet. So this is something we covered in previous videos, but electronegativity is just a measure of how strong does an atom pull electrons towards it. It has a lot to deal with the size of the nucleus, but also atomic radius as well. So this symbol is a lowercase delta. Usually we just use uppercase for Greek letters, but lowercase delta looks like that. And so delta plus is where we indicate a slightly positive charge, and delta minus slightly negative charge. Now again, it's not fully, we haven't made ions here. If the difference in electronegativity between two elements is greater than 2, then it will form an ionic bond, but in molecules they don't. So we simply look at our periodic table here. Let's look at an ionic compound. So there is lithium, which has the electronegativity of just 1.0, and fluorine, which is 4.0. So the difference between them is 3. So lithium fluoride is an ionic compound. The lithium atom loses its electron permanently. We could look at calcium chloride. So calcium again is 1.0 and chlorine is 3.0. That's the difference of 2. Calcium chloride is an ionic compound. But all others, so we could do water. The difference between the electronegativity of hydrogen and oxygen is only 1.4. So it forms a covalent bond. There we have it. So the polarity of a molecule can be, it can vary. Small molecules, they'll be, positive on one side, negative on the other side. Water is sort of like that. Whereas large molecules, because they don't really have certain molecules sort of form a line, but other larger molecules form more of a three-dimensional shape. So in those cases, there'll be like a region of negativity on the outside or positivity on the outside, and then opposite on the inside. But if a molecule has two negative sides and then a positive side in the middle, for example, that's called a dipole. So let's look at examples of these. So the carbon dioxide molecule is a dipole. The oxygen atoms are on opposite sides, so there's two negative ends and it's positive in the middle. The water is sort of a dipole, but because it's bent, it really has just one region of negativity and another region of positivity, if we can call it that. Here's an example of a molecule where the negativity, the slight negativity, surrounds the entire molecule. Chlorine is a much larger atom than carbon, so the electrons are more likely to be found around the outside. The middle region is slightly positive. Because molecules can be polar, they can attract each other without bonding. So these are known as intermolecular attractions or intermolecular forces, and they are not bonds, they are weak. You can think of them like static electricity. Rub a balloon on your hair and it'll stick to the wall, but it's not bonded to the wall, it's not glued to the wall in any sense, it's just attracted. So the weakest kinds of attractions are known as van der Waals forces, and they're named after a guy named Johannes van der Waal, and I'm probably pronouncing that slightly wrong. But dipole interactions occur when polar molecules are attracted to one another. So you can think of them like nanomagnets, tiny little magnets. The positive end of one atom or the positive end of one molecule and the negative end of another molecule hold them together. So this is hydrochloric acid. So this is an example of the hydrogen is positively charged, the chlorine is slightly negatively charged, and so these molecules tend to cluster themselves together for that reason. There are what are known as dispersion forces, and these are caused by the actual movement of the electrons. Now again, electrons are not, they're very complicated, but you can think of them as moving around and being in different places. Really, it's just a probability function of where they are. But not all polar molecules have these dispersion forces. So what happens is the movement of an electron in one atom, one molecule, can influence the movement of electrons in the neighboring molecule. Remember, electrons are negatively charged. So the probability or the location of one electron can push away, can alter the probability of where you find a neighboring electron because they're both negatively charged. They repel each other. And that, I believe, is what I said. This is the weakest kind of force, but with the halogen elements, it's very influential. We'll discuss that in just a second. So let's imagine these two atoms right here, atom A and atom B. So there are the electrons between them. So if we imagine, in one instance, this is the location of the electrons. In the next instance, the two electrons of atom B have a high probability of being over here. Well, that pushes away the electrons in the neighboring atom. So we see here, this just briefly has a very slight negativity towards one side of its sort of atomic radius, and then very slightly positive over here. Well, that pushes away those electrons. So that's what we're seeing here. You can think of it like just a mass of people in a mall or something. When you get too close to somebody, they kind of walk away from you a little bit. But if you're far apart from each other, your motion really doesn't influence the motion of other people that are maybe like 10 feet or more away from you. So here we can see in an instantaneous snapshot, this helium atom, I guess they're showing us, has, the electrons are over to this side, so it's slightly negative and slightly positive over there. Well, that causes the electrons of the neighboring atom to maybe pull towards that side a little bit more. So we would imagine that this is just constantly shape-shifting right before us. Now, why does this matter with the halogen elements? Well, fluorine and chlorine are gases. The larger the atom, the more electrons it has, the stronger this influence becomes. So with fluorine and chlorine, it's fairly weak because they're small atoms with not very many electrons. Bromine has many more electrons. Bromine is one of only two natural liquid elements, are, well, at normal temperatures on Earth, I should say. With mercury being the other. Bromine, though, will evaporate very rapidly, but it does form a liquid. Iodine, you probably think it's a liquid, but it's not. It's actually sort of a very dark, solid material. You always see iodine dissolved in water, but it's actually a solid, and I believe that's acetine, I think is that element. But these two elements are solid, this one is a liquid, and then these are naturally gases on Earth because of the difference in strength of those dispersion forces. The final one, hydrogen bonds. It's not a good name. These are not a bond. They're a type of dipole interaction. So the hydrogen electron is not shielded from any outer electrons. It has none of that atomic shielding, which we've covered before. So hydrogen bonds are stronger than any other kind of intermolecular force, intermolecular attraction, but they're not a true bond. So to illustrate, they're very weak, but they're just much stronger than van der Waals forces or dispersion forces. They have about 5% the strength of a covalent bond, which is, appreciable, which is significant. So, for example, water has the hydrogen and the oxygen atom, and water has many unique properties like capillary action, surface tension, and adhesion-cohesion. Water will form droplets that clump together. You try that with alcohol and it doesn't work. Alcohol will drip water on a slanted surface and the water will cling and form balls and not run down the surface until it gets quite large. Whereas alcohol, which is a non-polar molecule, will skate right down a surface right away. It does not have these properties. So I actually just learned this yesterday from watching another YouTube channel, but hydrogen bonds can only form between nitrogen and hydrogen atoms, oxygen and hydrogen atoms, and fluorine and hydrogen atoms on adjacent molecules. So here's a little bit what this looks like. The hydrogen atom, slight positivity, the oxygen atom, slight negativity, so they will be attracted towards one another. They're pulled together, but not truly bonded. And again, that can only happen between hydrogen and oxygen, hydrogen and fluorine, or hydrogen and nitrogen. So if you'll remember, when we covered ionic compounds, they almost always form solid crystalline substances. But covalent molecules, well, they form solids, but also many liquids and many gases. So there's a huge variety between them. The reason that covalent bonds come in such wide varieties of physical states is because of intermolecular attractions. They're repelled from each other or they're slightly pulled together. All the things we've discussed today. But there are some substances called network solids, which are covalent compounds, but they have unusually high melting points. So diamond, for example, carbon doesn't really form ionic compounds, it only forms molecules. So diamond is technically a molecule, but it has this extremely high, you can't actually melt diamond. It goes from solid sort of directly to gas in a way. We call that vaporization, and it's an insanely high temperature. And then there's also silicon carbide, which is used for extremely high-end vehicle car brakes. It's like a car that has like a $5,000, $10,000 brake option, like a Lamborghini or a McLaren or something like that. Will maybe have silicon carbide brakes, and its melting point, again, extremely high. Very, very fast cars under a lot of braking generate quite a lot of heat, so silicon carbide is a useful compound to make brake rotors out of. And that concludes this video, that concludes this chapter, so we'll be moving on to new things next time. Thanks for watching.